let me do example 2a in the textbook. If you have the textbook, you can follow along from there. If you don't have the textbook, here's the problem. Suppose that it is known that the number of items used in the factory during a week is a random variable between page 389. So all we know is the mean value of this random variable. What can be said about the probability that this week's production will exceed 75. So without much information, can we still say something about this probability? So the question is, what's the probability that this week's production X is greater than 75? X is a quantity that's produced, so we know it's non-negative. We know it's mean, so we can use the Markov inequality. So by the Markov inequality, this is just the expected value of X over 75. That's 50 over 75. So this is just Markov's inequality. So with very little information, we can still get some bound. We get an upper bound on this probability. That this probability will not exceed 2/3. Question, if we add in a little more information, the question says if the variance of a week's production is known to equal 25, then what can be said about the probability that the week's production will be between 40 and 60. So now we know the mean and we know the variance, so we know that we can employ Chebyshev's inequality. So put this question asking us, what's the probability that your x is between 40 and 50? 60. I see 40 and 60, these are numbers are sort of symmetrical about symmetrical distance, equal distance from 50, which is the mean. So let's subtract 50 throughout. Get 40 minus 50, x minus 50. And so we get the probability of x minus 50 is between negative 10 and plus 10. In other words, the probability that the distance of x from 50 is bounded at 10. But Chebyshev's inequality is in the other direction, probability of this distance being greater than or equal to something. we write this as 1 minus probability x minus 50 is greater than or equal to 10. Now for this we can use Chebyshev's inequality. So Chebyshev's inequality tells us that this probability, x minus 50, the probability that it exceeds is greater than or equal to 10, is bounded above by variance of x. Okay? The variance of x now we've been given is 25 over 10 squared. So I'm just using this statement, so Chebyshev's. So this is 25 over 100, that's 0.25. So if this amount is less than 0.25, then 1 minus that is greater than 1 minus that. So if this number cannot exceed 0.25, 1 minus something that's less than equal to 0.25 is greater than or equal to 1.75.
But if we knew this was a normally distributed function, we could have
just
done it perfect.
right, exactly, yes. So if you have more information, like the exact distribution, then you can calculate this exactly.
That's really the 10 or
10 or 8. Here, this is greater than or equal to 10. This is 10?
Yeah.
10. All right.
Oh, 80 minus 50, is that what you're looking
That's 80.
80 minus 50 in the brackets at the end? Oh, it's 60. Shoot, never mind. I was just trying to help.
60, yeah.
In the first one, why does the inequality change to, when it's x, I mean, it should exceed 75, so it shouldn't, I can't figure out why it's exactly 75. Like, should there be an equal to sign as well? Like, it should be x.
Strictly greater than or equal to, well.
Yeah, can you switch that?
Yeah, I mean, yeah, I wouldn't be too particular about whether you included that or not.
Okay.
Okay, so, sorry. If you, let me see. When I defined this, did I take it as, define it as 1 if x is strictly greater than a, then x over a. Yeah, I don't distinguish between the two.
Why don't we use standard deviation here to do the probability? Shouldn't we divide by standard deviation?
Our statement here is that this probability is less than or equal to variance over c squared. That's all I'm doing. So all I'm trying to do is try and bring it into this form. I just want to bring it to the form probability that the absolute value of x minus mu is greater than or equal to something. So I first bring it to the form that probability that absolute value of x minus mu is less than something, and then greater than or equal to. If you want to know about whether I should include this or not, we have to go back to the proof as to greater than or equal to.
So that's the
Yeah. Strictly less than a, less than. Yeah. Okay. Okay. So in the way we proved it, for the Markov's inequality, if I have this, then I get this.
Okay.
But anyway, this is always less than or equal to, so you don't have to worry about that. So if you actually did the proof, then you would have got strictly less than. But strictly less than, you can write it as less than equal to. So you don't have to worry about whether you include it or not. This is always less than or equal to. And this also, because strictly less than equal to.
Gotcha.
So don't distinguish between whether you put equal or not.
Right, thank you.
And since I phrased it as will
Yeah, that was
exceed
correct.
75, so, I mean, it's strictly greater than, but as I said, this bound will not change.
Thank you.
For these markup inequalities, does that apply for both continuous and discrete cases?
Yes, yes, because our proof didn't use anything about whether it's continuous or discrete, yeah.
Okay. And given that that's true, in a case like this, if we wanted to be slightly more precise, could we use continuity correction?
No, I mean, that's nothing that helps with the proof at all. Because all the proof said was, I define it as 1, my indicator function is 1 if I can say either if x is greater than or equal to a, or x is strictly greater than a, but as I said, if I took it as x strictly greater than a, I get this, and I get less than or equal to. So there's nothing like continuity correction or anything coming to the picture here. I'm not approximating this by something, I'm not approximating something discrete with something continuous. That's the only time we have continuity correction. Okay? So I'm just giving an upper bound, that's it. Okay?
Right.
So yeah, so there's nothing like a continuity correction here.
Okay.
Okay.
Yeah, I was thinking not in regards to the proof, but for example, we're looking at you have to produce at least 75, and so that's the same as greater than 74 and a half or 75 and a half, depending on the
But
direction.
is that, oh yeah, so items, yes, okay, yes. So,
And so in a case like that, would that still hold true?
well, yeah, I mean, sure, maybe you can make the bound just slightly better because you'd be dividing by something, you said that you can say greater than or equal to 76, then you get a smaller bound. Yes, that will help. Yes. Yeah, so if you can do something like this, sure, that helps. Because clearly if I divide by a larger number, I get a smaller number. So something like that, sure, it can help you get a more accurate bound. You're right. But not exactly a continuity correction. It's just that you can be clever about getting bounds. Right, exactly. Yeah.
If 40 and 60 didn't differ from the mean both by 10, could we still do this or no?
No, because you have to get it in this form.
Because it has to be the absolute value of it.
Yeah.
Okay.
The,
So
the
then what-
distance from you.
So what would we do there? We wouldn't be
The
able to
distance from me?
estimate it off.
Maybe then you could say, let me get you an estimate just for this part, and then for the remaining part, see, supposing it was probability that x is between 40 and 80.
Okay.
So I could do 40 and 60, and then plus the probability that x is between 60 and 80. I can bound it by the probability that x is greater than 60, and try and bound that. You know, you can do something like that, but I'm not going to ask you about stuff.
No? Okay.
Yeah.
Did you say distance from you?
Yeah,
From me.
distance from you. So that
From me?
yeah, mu is the
From
mean.
me.
Yeah.
Okay.
So,
Sorry, I'm sorry.
mu is the mean.
I won't do it
but
again.
Every time I say mu, I basically mean mean. Okay. So, okay. So you always have to write it in this form to use Chebyshev's inequality.
All right.
And things like this. Yes, if you your aim is to try and get as good a bound as possible. So as he said in this case, you notice that whether he said strictly 75 or greater than or equal to 76, it wouldn't have mattered. Okay? So continuity correction would be, oh, it would be more accurate if you put 75.5. That's not the case here. It's just that you know that you can do this, so you might as well use 76. Okay? That's the only difference. Okay. All right. What else? Okay. Did we finish the problem? Yeah, okay, fine. So all we can say here, we get a lower bound on this probability. So we know that the probability that x is between 40 and 60 will be at least 75% or more. Okay? So maybe this is quite useful because it tells us that, well, this probability is going to be pretty large. It's more than 75%. All right. I'll leave example 2b as homework, example 2b, which is on page, I mean, just read it at home. 390?
2B might be.
Into 390. So example 2B on page 390, that's basically an example that tells you that you can use the Chebyshev's inequality, but if you knew the actual distribution, you see that the actual value is so far away from the bounds that you get. So these bounds are not they're not optimal. But one thing, and I mentioned this, like Chebyshev's inequality, we will use it to prove the weak law of large numbers. And it turns out the Markov inequality and Chebyshev's inequality are very useful when you want to prove theoretical results. So one of the results we will prove, and this intuitively makes sense. If I tell you that I have a random variable and its variance is 0. Now the way I described variance, it was a measure of how spread out the values of the random variable could be, right? And if I say the variance is 0, that means they're not spread out, right? So it intuitively makes sense then that the random variable is just a constant, okay, with value equal to its mean. Okay. How do you prove that? Well, we can use our Chebyshev's inequality to prove that. Okay, so let me write the statement as if variance of your random variable you know is 0, then with probability 1, x takes the value its mean. Right? So otherwise, I can write it like this. Let me say mu. So mu is expected value of x. So we call that mu is expected value of x. So that means x takes the value mu with probability 1 and doesn't take any other values. X is just a constant mu. So the probability 1 takes just one single value and no other values. Okay, so proof of this. Remember some of your calculus proofs. If you want to show something very close to something else, you take for any epsilon greater than 0.
Oh boy.
Let's look at the probability of the distance. What's the probability that the distance of x from mu is greater than epsilon? That x takes some values other than mu. Okay? So x can take values of mu plus epsilon or more, mu minus epsilon or smaller. By Chebyshev's inequality, what is this? This is just the variance of x over epsilon squared. Right? But what is variance of x is just 0 over epsilon squared, so it's 0. So no matter what epsilon I take, if I ask, does x take any value more than epsilon distance from mu, I get the answer, the probability is 0. Okay, so if it's bounded by 0, this is obvious. Probability is always greater than or equal to 0. Now I have by Chebyshev's inequality is bounded above by 0. Therefore, this probability this is true for all epsilon greater than 0. Let's take your limit at epsilon goes to 0. So this is true for every epsilon. Then as epsilon goes to 0, it's still true. It's still 0. Oh, okay, I'm not going to write that last time. So basically, if you take the limit as epsilon goes to 0, probability that x, this just gives you probability that x equals mu. I mean, probability x not equal to mu. All right, so I know that for no matter how small I make epsilon, the probability that x minus mu is greater than that epsilon, that's always 0. So x minus mu is always within epsilon distance. X is always within epsilon distance of mu. I can shrink epsilon, and then I get that x can only be mu. Right, so for each epsilon, I've proved that that x can only take values in here, right? Because probability of being out here is 0. Shrink your interval, and then that means x can only take values out here. So x can finally take epsilon goes to 0. Okay.